So this will be Lecture 5, Part 2. A continuation of our discussion of polar coordinates and polar plotting. And so what do we talk about here? So let me pull up the lecture note. So we're going to be talking about graphs of polar equations. So here's and we'll do it by example. So for instance, suppose we want to graph the polar equation r is equal to 3. Okay, and we want to graph this in the polar plane. So one way of dealing with this, of managing this, is that we know that r squared, of course, is 9. Okay, and so if we were to replace r squared with its rectangular version, so we would have x squared plus y squared is equal to 9. Okay, and so you should recognize that this is essentially a circle centered at the origin of radius 3 in the xy plane. So the locus of points that make up a rectangular graph, as shown here, okay, so this is a rectangular graph, x squared plus y squared is equal to 9 with radius 3. The locus of points that make up this graph will be the same as the locus of points that will be portrayed in the polar plane, right? So to graph this in the polar plane, though, requires another type of consideration. So let me pull up our class calculator. Let me see if I can get it to work. It's a little bit tricky. So I'll go to another slide and insert a web browser. Let's see. 1 second. So, and so we're going to take the equation r equals 3 and we're going to plot it in the polar plane, okay, as opposed to the rectangular plane. So that's our objective here. So to do so, in this calculator tool, change your graph settings to a grid, from grid to polar. Okay, and right, and so when you do so, you'll see the polar graph paper will show up as a series of concentric circles. Now, this polar graph paper is also available, I believe, as the last page of the Chapter 5 lecture notes. So you can take the last page and print it out, print a number of copies out if you want to have some special graph paper for polar graphing, because we're going to get rather heavy into this momentarily. So now, the objective, of course, was to graph r equals to 3. Okay, and when you do so, you'll see the result is, again, in the polar plane, a circle of radius 3. So how do we know the circle is radius 3? Well, here's your polar vertex right here, and here's the radial arm length of 3 right there. See, it's delineated 1, 2, 3, 4, and 5. Okay, so very similar to the rectangular coordinate system, but you'll notice that there are no negative numbers along the polar axis, or on the axis perpendicular to the polar axis, which really has no name. Also note that when you graph r equals 3 in the polar plane, you're essentially the process would involve doing this. You basically go to the polar vertex and then go out on a radial arm length of 3, and then the implication is that theta ranges from 0 to 2 pi. Okay, and so as theta ranges from 0 to 2 pi, you draw a radial arm length of distance 3 for each value of theta between 0 and 2 pi. And when you do that, you'll accomplish having drawn a circle of radius 3 in the polar plane. So when r is equal to a constant in the polar plane, r is essentially the radius of a circle centered at the polar vertex, right? So that would be the most fundamental of polar graphs. Now, what happens if theta is equal to a constant? So that's a little bit tricky, and unfortunately, I don't think it works with this tool. Okay, nothing happens. I've tried it. So if I were to try, say, theta is equal to pi halves, or theta is equal to pi thirds, say, theta is equal to pi thirds. Nothing happens. Okay, the tool fails. Or maybe try theta is equal to 60. Say theta is equal to 60 degrees. Nothing. Okay, so this calculator throws up when you do that. So let me tell you how to do that. So let's go back to r equals 3. It does r equal constants, okay, but it doesn't do theta equals a constant. Okay, so there's r equals 3 again shown in purple. Now, for theta equals to a constant, here's the rule for graphing that. Okay, sorry about that. Let me zoom out. Okay, so shown in black is r equals 3. All right, and so we pull up the pen tool, and we want, say, theta is equal to pi thirds. So let me show you how to sketch that graph. All right, so first of all, we don't have a radial arm length. So what you'll do is, okay, say make up, say r is equal to 1, or r equals to 10, okay? So, well, don't even do that. There's an even easier way, sorry. All right, so first of all, just identify an infinitely long radial arm starting at the polar vertex that goes in the direction of pi thirds, okay? So this is one branch of the graph of theta equals pi thirds. So theta equals pi thirds represents the locus of points which have an orientation of pi thirds radians. Now, it turns out that theta of pi thirds, you also have to extend it infinitely in either direction. So once you graph this ray, then you have to reflect this ray about the polar vertex as well. That's the rule, right? Okay, so we have to reflect about the polar vertex. So you start off by drawing theta equals pi thirds in this direction, and then you'll reflect it about the polar vertex in this direction. So it's kind of tricky to draw. So let me line it back up. So you'll reflect it this way. And the reason being is that you could have, say, a point negative r pi thirds, okay? And of course, if, well, not even that point. Let's say if I give you a point negative r pi, let's see, how would I do it? Yeah, if I give you a point negative r pi thirds, okay, then the process of plotting, all right, so let's say, suppose I gave you, to demonstrate, suppose I gave you a point, say, negative 10 pi thirds, okay, so clearly this would be a point, this would be a point with theta equals to pi thirds, okay? And so theta equals pi thirds is the locus of points where the ordinate is pi thirds. So now how will we plot 10 negative pi thirds? Okay, well obviously negative 10 has a theta of pi thirds, but where is it in the polar plane? Okay, so to do so, remember the procedure? We go out a radial arm length of 10, okay, then we rotate pi thirds, okay, and so the coordinate of this point would be P10 pi thirds, okay, and then we take the point and we rotate it pi radians, okay, rotate it pi radians until you come back here, okay, and so the coordinates of this point would be P negative 10 pi thirds. All right, so again, the points here along this ray of the line theta equals pi thirds all have ordinates of pi thirds, but their abscissas are all negative. Okay, so this is the justification for theta equaling a constant. All right, so that's one way of graphing theta equals to a constant. All right, so what else? Okay, so let's consider the graph r equals 2 sine theta. Okay, now to do that, let me pull it up. We can use a function table. That's one alternative, but it's not the most efficient way. But it's okay to do it that way. But with more complicated functions, of course, you want to try and not have to rely so much on function tables. So for topic 3, okay, let's talk about a graph of r is equal to 2 sine theta, because there is a generalization that we can make when graphing sine functions and cosine functions in the polar plane. All right, so topic 3. We want to sketch the graph of r is equal to 2 sine theta. So the approach is basically build a function table of first quadrantal values. In other words, take your familiar angles, pi 6, pi 4, pi thirds, all the way up to pi. These are our familiar angles. And then calculate the radial values, 2 sine theta. All right, and so you should know how to fill in this row of the function table. And then essentially take each point and plot them in the polar plane, as shown in these. Each of the dots here, or will be each of the points plotted in this graph, would be the points from the function table. And then you would essentially connect the dots, and you'll see that it forms a circle. But there's a more concise way of, if you recognize the format of the function, it's r is equal to some amplitude times sine theta. And there's a rule. It turns out that if r is equal to 2a sine theta, okay, this will be a circle with radius absolute value of a, okay, remember a can be negative, centered at a equals pi halves. So in this specific case, a is 1, and the center of the circle would be at 1 pi halves. So you note that 1 pi halves is right here. Okay, if we were to plot the point in the polar plane 1 pi halves, we go out 1 radial unit 1, okay, and then rotate pi halves, and that would be the center of the circle. And then the radius, of course, is 1. So we just draw a circle with radius 1 here at the center in the polar plane. Okay, all right. Now, if r were to say to equal to 2a cosine theta, this would be a circle with radius a, absolute value of a, centered at a0. So so that we can compare and contrast now. So let's sketch a cosine theta versus sine theta plots in the polar plane. So let me go to this page. Erase the content. Okay, and set the graph style to polar. Polar graph paper, and then we'll say r is equal to 2 sine theta, like so. Oops, I misspelled theta, didn't I? Theta. All right, and you can see there's the circle centered at 1 pi halves. See if I can zoom in. All right, so you can see how it's done. Now, according to the note from the previous slide, if we were to graph r is equal to 2 cosine theta, then the center of the circle, r equals 2 cosine theta, would be at the point 1, 0. So compare and contrast. R is equal to 2 cosine theta. And that'll be shown in blue, okay? And so, as you can see, it's the circle centered at 1, 0 of radius 1, right? So the two circles, sine theta and cosine theta, translate into circular plots in the polar plane, all right? Okay, so that's one facility that you should have now for graphing polar equations, the basic ones. So let's see, topic 4, a little more interesting, more involved now. Suppose we want to graph this function. Let me extract a copy of it from the notes. This would be topic 4. And I'll show you the procedure for how to plot. All right, so here's our problem. We want to graph in the polar plane, r is equal to 2 plus 2 cosine theta. Well, the procedure would go as follows. Identify, or in other words, sketch the graph of the function from 0 to 2 pi, okay, as if you were in the xy plane. All right, so here we've sketched the graph r equals 2 plus 2 cosine theta as if we were in the xy plane. And so you would know that basically the period would be 2 pi, and it's basically the cosine graph. So to do so quickly, all right, the fundamentals here, so you know the cosine graph would look like this, between 0 and 2 pi. So this would be 0 pi halves, right? And then this would be pi. This would be, of course, -1 here. And then this would be 3 pi over 2. And then this would be 2 pi. All right, so this would be y, the black is shown as y equals cosine x. Okay, now to plot y equals 2 cosine x, you just extend the amplitude, multiply the amplitude by 2. So you can just change this to 2. Okay, so this graph then is y equals 2 cosine theta. And then finally, all you have to do is to get 2 plus 2 cosine theta, you take the black curve and you shift it up 2 units. And that's shown right here in the orange curve. So convince yourself that this orange curve is the sketch of 2 plus 2 cosine theta. So now, to plot this, what you'll do is you'll divide the interval 0 to 2 pi into 4 equal length subintervals. Okay, so we're going to plot this in the polar plane. All right, so from 0 to pi halves, okay, the sketch in the polar plane of r equals 2 plus 2 cosine theta would basically be this content right here. So you take the locus of points defined by this green arc and you'll plot it in the polar plane. So let's see here. Let me insert a web tool and I'll show you what it would look like. So it's a piecewise kind of, oops, not there. Let me go back. This one. I didn't want to, I wanted to extend the page, not create a new page. So insert internet browser. Oh, what is this doing? So let me trying to get both display on the same page. It's a little bit challenging. All right. Okay, so now we'll go to our calculator tool. And we'll switch to our graph paper mode to polar. All right, and what we'll do, as I suggested, okay, we take this portion that's accentuated in green, and we'll overlay that in the set of points accentuated in green. We'll overlay that in the polar plane. So we have y. I'm sorry, not y, but r. R is equal to. Why is it doing this? R. Oh, jeez. Thinks I'm on the typewriter tool, doesn't it? So I'm not sure if I'm going to have any success with this. Okay. So R is equal to 2 plus 2 cosine theta. Now theta is between 0 and 2 pi. Right, so what will the sketch of that look like, assuming that it'll... Did it plot? It didn't plot, did it? Oh. R is equal to 2 plus 2 cosine theta. May not. So let me get rid of this. Let me see if it'll let me go into grid. It's not letting me. Okay, so this isn't going to work. Okay, all right. So I have an alternative way. Let me pull up the copy of the graph paper from the online lecture notes. I don't know. Somehow these operating system updates are really not functioning well anymore. Okay, so let's do it old school way. All right, so here's our polar plane, and what we do is, okay, so between 0 and pi halves, okay, so at 0 we start off at 2. Okay, so we first plot the point. So if we say this is 2 right here. So at 0 we start off at 2, and then at pi halves we end up at, no, I'm sorry, at 0 we start off at 4. Sorry, I beg your pardon. At 0 we start off at 4. So 1, 2, 3, 4. 0 we start off at 4. And then at pi halves we advance to 2. So 1, 2. Right, and then we just connect the curve as shown in the rectangular curve. So this curve will have the same shape as the shape of this green portion. Okay, and so we connect 4, 0 to 2 pi halves. All right, now from pi halves to pi, what we'll do is we'll connect this portion of the graph. So pi halves to pi. So at pi halves we're at 2, and at pi we go to 0. So at pi is here, we have to come around, mimicking the shape of the rectangular sketch to do like that. So we have to connect those 2 points in the shape similar that's drawn in the rectangular portion. Now from pi to 3 pi over 2, we range from 0 to what? At 3 pi over 2, we're at 2, right? We're back to 2. So that would be right here. So mimicking the shape of the red arc in the rectangular plane will produce that in the polar plane. All right, so we go from 0 pi to 3 pi over 2, 2. Okay, so 3 pi over 2, 2 is where? So here's 3 pi over 2. That would be right here, correct? Okay, so mimicking the shape, we would do this, right? So we sketch that arc. And then from 3 pi over 2 to 2 pi, we range from 2 to 4. Okay, so that would be the blue arc. Mimicking this shape will produce that shape in the polar plane. So it would be, we connect the final two dots, right? And so there's your graph. And so this is called a cardioid because you can tell by the shape. And if we were to sketch, now if we were to continue on with the rectangular sketch for over several periods, then what would happen is translating several more periods of this sketch into the polar plane, you would just start overlapping again the segments that you've already drawn. Okay, so it repeats itself over and over. So you only need to sketch one period of the function in the polar plane to get the picture. So this is called a cardioid. Okay, cardi must have something to do with the heart. Cardioid. All right, so that's how that's done. So let's see, we can do another example. Now, before I move on, properties of cardioids. So we have the following. All right. All right, so for cardioid, is generally of this format. It'll be a constant A times 1 plus or minus cosine theta or sine theta. So whenever you see a polar equation of this form, you'll anticipate that the graph will be looking like this, but it'll be rotated based on the value of A, whether you do a subtraction and whether you do a sine or cosine. So I think there's a summary table in the text that tells you the orientations of cardioids. Actually, I don't think there is. Okay. Yeah, you'll just have to investigate accordingly based on the procedure I've just offered up. All right. So now let's do another example of a polar plot. So let's say r is equal to cosine 2 theta. So let me extract that out. This will be topic 5. Okay, so we wish to plot this graph, r equals cosine 2 theta, in the polar plane. All right, what would it look like in the polar plane? So now, again, the procedure is we have to sketch r equals cosine theta on an interval from 0 to 2 pi. And of course, you should recognize that cosine 2 theta has a period of pi. And so how do we know that? Well, we take 2 pi, remember from chapter 2 lecture notes, the period of this graph would be 2 pi over 2, which is pi. All right, but we have to sketch 2 periods because we're required to sketch the graph from 0 to 2 pi. Now, remember how to sketch the cosine graph, cosine 2 pi from 0 to pi? Okay, identify one period and then divide the 1 period interval into 4 equal length subintervals, and then just sketch the graph of the cosine function on these 4 subintervals. So we know on the first subinterval, so on any first quarter length interval, for the first one, the cosine function transitions from 1 to 0. Okay. On the second quarter length interval, the cosine function transitions from 0 to -1. Okay. So here's our second quarter length interval. And as always, cosine will transition from 0 to -1. And then on our third quarter length interval, the cosine function transitions from -1 to 0. And then on our fourth quarter length interval, the cosine curve transitions from 0 to 1. All right. So that's how we sketch the cosine 2 theta on 1 period. And then since we have to sketch the graph from 0 to 2 pi, we just do a periodic extension to get this. So now, what would its graph be in the polar plane? That would be an interesting question to pursue. So let me paste in the polar graph paper. So let me pull that up. So where's my polar graph paper? I think I've got it somewhere around here. Okay, so I'll paste it in here. So here's our polar graph paper, and we'd use essentially the same procedure from the previous example. So we start off by saying, okay, as theta ranges from 0 to pi fourth, how does the R value change? Okay, so from 0 to pi fourth, we see that R ranges from 1 to 0. So we'll reflect this portion of the graph in the polar plane. So from 0 to pi fourth, okay, how about we make, for our emphasis, we make, say, we scale our drawing, so this would be, we'll call this 1, okay? Since our amplitude is 1, and so I can supply more detail. So assuming this is 1, so at 0, at theta equals 0, R is equal to 1, and at theta equals pi fourth, R is equal to 0. So this is actually tangent here. This red arc is actually tangent to the line theta equals pi fourth. So that would be the sketch shown here. Now, from pi fourths to pi halves, R ranges from 0 to -1. Okay, so at pi halves, we would have the coordinates, let's see, 1, 0. So we would have -1 pi halves, like so. Okay, now, how do we complete the graph for this section? Well, the strategy is, when you're doing polar plots, plot only positive values for R. Okay, so note that -1 pi halves is this point. Okay, now when doing polar plots, you have to convert the negative abscissas to polar abscissas. So that means if we were to do that, then we would have to rotate 180 degrees, like so. And so -1 pi halves is equivalent to the point 1/3 pi over 2. Okay, and so this would be the destination point. So you start where you left off, and then you would do this. You would connect the points like that, because you only work with positive distances in the polar plane, in polar graphs, okay? So that's a rule of thumb right there. Okay. All right. So you're actually doing that. All right. Okay, so let's see what's next. Okay, so now we sketch the graph. Okay, let's go back to our reference. We sketch the graph from -1 pi halves to 3 pi over 4. Okay, so where's 3 pi over 4? So 3 pi over 4 is here, and we have to go to 0 at 3 pi over 4. So noting that the line theta equals 3 pi over 4 is this line right here. This is theta equals 3 pi over 4. We need to go from this terminal point to 0, 3 pi over 4. And so that would bring us back here, like so. Okay? All right, what's next? So I can erase this reference line. Okay. That's because that's not part of our graph. That will not be part of our graph. So next, we go, okay, so that was this part. So next we go from 3 pi over 4 to pi. So in this case, our R value ranges from 0 to 1. So at pi, we'll be at 1. So that means we pi will be, this is 1 right here. So we go tangent to the ray 3 pi over 4, and we go here. So we complete that arc right there. Okay. Then from, what color have I not used? I haven't used black yet. Okay. Then we go from 1 pi to 0 pi, 5 pi over 4. All right. So where's 5 pi over 4? So 5 pi over 4 is right here. So we have to go back to 0. And so we're essentially staying tangent to 5 pi over 4. So we come back like so. Okay. So that would be the next arc you would draw. And then we go from 5 pi over 4, 0, 5 pi over 4 to negative 1, 3 pi over 2. So negative 1, 3 pi over 2. All right, so we would have to convert that to a positive radial arm length. So first of all, plot negative 1, 3 pi over 2. All right, so to plot negative 1, 3 pi over 2, we first identify 1, 3 pi over 2. Well, we first identify 1. Okay, so the procedure is you identify 1, like so, and then you rotate it to 3 pi over 2. Okay, so this point right here is 1, 3 pi over 2. So negative 1, 3 pi over 2 means we rotate counterclockwise pi radians. Okay, so rotate counterclockwise pi radians, like so. And so the coordinates of this point would be negative 1, 3 pi over 2. All right. So let me see. Okay. All right. So we've identified negative 1, 3 pi over 2. So that would be where we would have to go. So let's check that. Yes. All right, so negative 1, 3 pi over 2 being there, we start at the origin, the polar origin, and then we go like this. Okay. Like so. So we make an arc like that. All right. Okay, so what next? So we've accomplished. So we've done this piece, right? Okay. Now we go from negative 1, 3 pi over 2 to 0, 7 pi over 4. So let's do that in black. So where's 7 pi over 4? So 7 pi over 4 is basically, where's 7 pi? Right here. Okay, so we have to go to 0, so we would come back around like this, being tangent to 3 pi over 4. So we're tangent to here. So we would have that piece. Okay, so we've taken care of this piece. And now we go from 7 pi over 4, let's see, we go from 0, 7 pi over 4 to 1, 2 pi. And so we can do that in, say, what color? Oh, we've used all the colors. So we need to go 1, 2 pi, which is 0. Let's see. We go from this point to, let's see, 0, 7 pi over 4 to 1, 2 pi over 4. And we're always going to flow in a counterclockwise direction. Yeah, we always draw our arcs. Oh, that's one thing I should note. We always draw our arcs in a counterclockwise direction. The reason why I'm saying this is because, well, I can get confused here. Why not just retrace this red arc? Well, if I retrace the red arc, I'll be going in a clockwise direction, right? So whenever you draw arcs in the polar plane, always draw your arcs in a counterclockwise direction, okay? And so that would complete the circuit like that, right? So now we've just traced from 0 to 2 pi. So go back through this, the notes again, and note that I've always drawn my arcs in a counterclockwise direction. Okay, always go this way. That's why you don't end up retracing existing arcs, because if you retraced an existing arc, you would be going clockwise. So that's the technique. I don't think the book mentions that. All right, and so this is called a four-leaf petal, a four-petal rose. Okay, so anytime you have a modified period of a cosine or sine function, you're essentially going to end up with a four-leaf or a four-petal rose. This is called a rose, in which case we have four petals. All right. Okay, so topic 6 then regards another technique we can use for sketching graphs of polar functions or polar graphs. So let me paste that in here. And we'll use this technical note to sketch another polar equation in the polar plane. All right, so we have polar graph symmetry. In as much as we have symmetry in the rectangular plane, we have symmetry in the polar plane. All right, so polar graph symmetry. If a polar equation is unchanged when we replace theta by negative theta, then the graph is symmetric about the polar axis. And that was the case in the previous graph. That's also the case with, say, where else do we see that? For r equals a constant. Okay. Now, if the equation is unchanged when we replace r by negative r, the graph is symmetric about the polar vertex. And that was the case in the previous example as well. And it's also the case with theta equals a constant. Okay. So basically, yeah. If the equation is unchanged when we replace theta by pi minus theta, the graph is symmetric about the vertical line theta equals pi over 2. And that was the case in the sine plot. An example of this would be y is equal to, no, r, not y, r. R is equal to sine, say, 2 sine theta when we did that example. Okay, that graph was symmetric about the line theta equals pi halves. About the vertical line theta equals pi halves. Okay, so these are, I don't expect you to memorize these, but if you happen to think that there's symmetry in your polar graph, then you can refer to this topic and use it as a foundation, as a guide for checking the symmetry that is in your sketch for verification. All right, so let's do this one now. Let's do another polar sketch, polar plot. Let's sketch r is equal to 1 plus cosine 2 theta. So let me paste that in to the smartboard interface. Okay, don't save. Okay, so in this case, r is equal to 1 plus 2 cosine theta. All right, so we can check the symmetry. So when we replace theta by negative theta, the graph is unchanged because we know the cosine function is an even function. And so therefore the graph should be symmetric about the polar axis. Now to find the, okay, so here I'm just calculating the zeros. We solve the trigonometric equation 0 is equal to 1 plus 2 cosine theta. And using the techniques from chapter 4, of course, we can see that where theta is equal, cosine theta is equal to -1/2, would be the solution to the equation, and that makes theta equals 2 pi over 3 and 4 pi over 3. And of course, we have to sketch the graph from 0 to 2 pi for our polar plots. And here's the sketch, okay? And equations of the form a constant right here, a constant plus or minus an amplitude times a cosine or a sine function. These are called limosans, okay? They're almost like cardioids, but there's a subtle difference, okay? So let me show you. So I have an expectation that you can get the rectangular graph of Rx equals to 1 plus 2 cosine theta from 0 to 2 pi. So now let's trace the polar graphing, how you would proceed with that, how you can understand it. All right. So if I can ever, so let me paste the polar graph paper into whiteboard. Right here. Okay. So for some reason it wants to snap. Okay. So now from 0 to pi thirds, we see that the output of the function ranges from 3 to, what's the value of pi thirds? At pi thirds, cosine of pi thirds is a half. So this would be 2, right? So the output is 2. So we'll call this cosine. Yeah. So the coordinates of this point would be pi thirds. Theta equals pi thirds, r is equal to 2. Okay, so we have that. All right, so at 3, we have 0. So if r is equal to 3, so here's r equals 3. I'll use 1 equals 1 scale. And then at r equals pi thirds, we have 2. So 2 would be, so here's pi thirds. So identify pi thirds 2. That would be here. All right, and then we would connect those two pieces like so. All right, following the shape of the graph. All right, now from pi thirds to 2 pi over 3, we range from 2 to 0. All right, so from 2 to 0. So at 2 pi over 3, we have to come back to 0. So going counterclockwise in my drawing of the arc, we do this. All right. Now from 2 pi over 3 to pi, we range from 0 to -1. All right. So now we do this piece. All right. So where is pi -1? All right. So to do that, we plot pi 1, which is here. Okay. There's pi 1. Or excuse me, 1 pi. R is equal to 1. Theta is equal to pi. And then we rotate it 180 degrees, and we come here. Okay, and so this would be -1 pi, which is the point that's our destined point. So we connect the two dots going counterclockwise, so we'll have this arc right there. Okay, all right. Noting that it's tangent to, probably it's going to be tangent to pi, this radial arm 11 pi over 6, because that's the midpoint between the two. All right, that's 11 pi over 6 right there. Okay, now from pi to 4 pi over 3, we range from -1 to 0. So at 4 pi over 3, where's 4 pi over 3? 4 pi over 3 is this radial arm. We got to be 0 there. So we have to go from this point back to 0, like so. All right, so that would be this green piece right there. Now from 4 pi over 3 to 5 pi over 3, we range from 0 to 2. So that would be this piece in yellow. All right, so at 5 pi over 3, we need to be at 2. Going counterclockwise, where's 5 pi over 3? Right here. So 1, 2 on the theta equals pi thirds ray. So then we go counterclockwise in our arc drawing, like so. And this yellow will be symmetric with the red. Okay, now from 5 pi over 3 to 2 pi, we range from 2 to 3. So I'll go back to using black. So it'll be this piece. So we got to be at 3 at 2 pi. So 1, 2, 3. Here's 3, right? This is be 3, 2 pi. So we connect the dots like so. Okay, and so a limason has this little internal loop in the interior of the bigger section. So this would be an example of how you would draw a limacon. Now remember, all of the arcs were drawn in counterclockwise fashion. Okay, and notice how I plotted -1 pi. I was careful to plot 1 pi and then rotate 1 pi 180 degrees to get -1 pi. Okay, so that's the procedure. I kind of like this. It's an interesting topic. And it's also the end of this topic. Okay, so this will be Lecture 5, Part 2. And this will be the conclusion. So the next lecture, complex numbers. So go ahead and get started on your WebAssign questions. I think you may have a couple of polar plots to do, not too many. And as usual, if you have any questions, email me or see me. And don't spend too much time going through the solutions to the problems. If you're taking more than 10 minutes to answer a question, then seek guidance, either from a tutor or from me or from a web source. All right, so that will take care of this lecture.